All right, so now the last step, then it should be pretty easy. Yeah. So now we can find the, graceful way. Yeah. So we want to spread data copy in a, relatively long period of time. Yeah. So how to do it? Yeah. Remember, so when we hit the 90% line, yeah. So the capacity, yeah. So if I use this, suppose this array, okay, yeah, this is the whole array. This line segment representing whole array. The capacity. Our dynamic data fills the 90% of the capacity. Okay? All right. Still, there is 10%. So when a new data comes in, still there is some room. Yeah. But we need to do data copy immediately. Yeah. So this time we arrange the data copy in this. When one new data item in, we copy 10 data item, 1 to 10 ratio. How about that? 1 to 10 ratio. Okay? So when you get a one new data added into still the old array, here, still old array, adding 1, but we choose, in order, 10 old data we copy into the new array. Yeah. But when you copy 10 data, you do not need much time, right? Only 10. 10 data item copy, several milliseconds, so your users won't notice that. Yeah. Another one new data comes in, then another 10 old data items copied, and so on. Yeah. But remaining, you have room for 10%, right? You have room for 10%. 10% corresponds to 10 times of 10%. Is it 100%? Yeah. So after you finish that 10% of the space, you copy the 100% of the old data amount into the new array. Then you can drop the old array. After you completely copy the older data into the new array, then you can destroy the old array to release the space. Yeah. But during the whole copy period, nobody can notice that. Nobody can notice the difference. Yeah. The delay just, milliseconds level delay. Nobody can notice that. Yeah. So that's the idea. So when you handle the dynamic data. Yeah. All right, so let's do the remaining, the heap property. Now we want to look at the heap properties and operations. Yeah. All right. Relationship among heap nodes. Now we want to define parent-child relationship. All right. Before we define parent-child relationship, we cannot call it a binary tree. Yeah. But only after you define the parent-child relationship, then you can call it a binary tree, yeah, stored in an array. Yeah. All right. Each node, we know, corresponds one element in the array. We just use array index to access that node. Yeah. All right. Now, relationship between two nodes. When we study relationship between two nodes, we can study the relationship between their corresponding indices. Yeah. Two indices. Yeah. Yeah. All right. So now let's define parent-child relationship through their indices. Yeah. All right. So let's consider a typical triangle. Yeah. 3 nodes. Yeah. P, parent node, with index I. Okay. Left child, L, colon, 2I. Then we define the node with 2I index as the left child node of that P. Left child. Yeah. This relationship. All right. Right child, the element with index 2I plus 1, we make that position the right child position for this P node. That simple. Yeah. In this way, you can see, yeah, the locations of 2 possible child nodes. Yeah, 2 possible, yeah, because sometimes a node may not have the child node, right? Yeah. Sometimes a node may have the left child node, but no right child node. Yeah. All right. So but when you have a node with index I, you know where to find its left child node and where to find its right child node. So you can see in this simple arrangement, the whole binary tree structure can be stored in an array. That's simple. Yeah? Parent-child. So here you can see we do not use pointers, right? No pointers. Yeah? No pointers. Yeah. Only the index relationship. I to I, yeah. Those 2 locations, yeah. So we know, yeah, parent-child relationship. Yeah. That's simple. Yeah. So in this way, we can store a binary tree in a perfect way inside an array. Yeah. All right. But there is one special consideration we need to, be careful. We cannot use the array position with index 0. Yeah. The reason is very simple. Because if you double this 0 number, you still get a 0. Yeah? Then we do not allow its left child location to be the same as the parent node location, right? Yeah? We do not allow that. Yeah. So that means this location cannot be used in a heap. Yeah. Yeah. The reason, because this definition, this node will break this definition. Yeah. Yeah. But if we do not use just one node, then it's okay. Yeah. Only one element in an array cannot be used. Yeah. Yeah. So that's not a big loss. Yeah. So that's acceptable. Yeah. All right. Yeah. Then we need to add more properties. So this definition, we address the parent-child relation. It's still not enough. Yeah. In order to, because our goal, we need to do the heap sort. In order to make our data structure support the heap sort, we need to add more properties. All right. 2 types of heaps. First type we call the max heaps. Second type called the min heaps. Yeah. Max, so here you can see we arrange the nodes inside a heap based on different conditions. Yeah. Maximum, minimum conditions. Max, you can imagine when you to put the maximum value at the root position. The main heap, we need to put the minimum element at the root location. Yeah. And more, actually the max heap property. What's the max heap property? Yeah. For each parent-child, regarding the parent-child relationship, A of I, this is the value stored in the parent node, right? So the value stored in the parent node should be greater or equal to the value stored in its left child node. A of 2I, that's the value of the left child node. And the value of the parent node should also be greater or equal to the value of the right child node. If this condition is satisfied, we get a max heap. This must be true everywhere in this heap. Yeah, everywhere, for any index I. Similarly, the main heap condition, we just change the direction of the inequalities. Yeah, less than or equal to. Yeah. Yeah. Based on the applications, yeah, so you need to choose one of the two heaps. Yeah. And here because our goal, we want to sort our data in ascending order. Yeah, so we pick the max heap case. Yeah. If a descending order, then you need to pick the main heap to store your data. All right, now let me give you a max heap example. Yeah. So you look at this heap. Outside number, that's the index number. Yeah, we do not use index 0, so we index 1, 2, 3, and so on in order. So you can see in this natural order. All right, yeah. Then the numbers in the circle, that's the values stored in this array element. Yeah. All right, now you can check. Yeah. So how to check the max heap property? You need to consider all the possible triangles in all the possible local triangle. Yeah, it's a local triangle. Okay? Yeah. The value of the parent node 7 greater or equal to 1. So this is satisfied. Look at this triangle. The value 8 greater or equal to this 2 and 4. So also satisfied. Next one, you look at this local triangle. Value 10 greater or equal to 9 and 3. Yeah. And so here also, the last one here. Everywhere, the max heap property is satisfied. So we call it a max heap. If you find one violation, then we cannot call it a max heap. Yeah. All right, but we need to write this max heap in an array. So here I show you how to write it in an array. Yeah. Writing an array, this location we cannot put any node. Yeah, 0 location. Yeah. So location 1, yeah, we put element 16. Yeah. Then 2 child nodes, double this 1, that's 2 and 3. Yeah. So we put 2 child values, 14 and 10. Yeah. Then for node 2, yeah, index number 2, 4 and 5, right? So store value 8 and 7. Yeah. Node 3, 6 and 7, yeah, store value 9 and 3. Yeah. Node 4, 8 and 9, yeah, store 2 and 4. Yeah. Node 5, only 1 child, yeah, so we store value 1 there. So in this way you can see, yeah, although we need to work on a binary tree, but the underlying storage structure, it is just a plain array. Yeah. But this plain array, we need to use the parent-child relationship to connect the nodes in a binary tree. So when we apply our operations on this binary tree, we need to use this parent-child relationship to do our operations. That's the main difference. So in this way, you can see we do not need to use any pointers, references, linked list. So we do not need that kind of complex structures. So we just work on the indexes. So that's very easy. Encoding. All right. Next, maintaining the heap property. Because sometimes you may have some violation of the heap property. Max heap, min heap property, some violation. Because when you do insertion or deletion, then you may have a violation, right? So the question is, when you detect, first you need to detect the location of the violation. After that, you need to fix it. You need to, recover the max heap property. So let's consider those operations. All right. Let's consider the typical local triangle, PLR, this triangle. Suppose one violation occurs within this local triangle. All right. We need to, that means if we check the max heap property, one of the inequality is not true. One of the two inequalities is not true. All right? Then we need to fix it. We need to apply the swap operation to recover the max heap property. All right. So here let us assume, in this circle, it has a max heap. And the right subtree circle also max heap. We only consider this local triangle. All right. Local fixing operations. But after you do the local fixing, you solve the problem locally, but at the end you need to check for the violation globally. Then, after you fix all the violations globally, then you can say you get a max heap structure. All right. Now let's look at a local heapify operation. So it's a recursion approach. It's a recursion approach. Remember, here I want to connect to that in-place algorithm. Remember, because we want to make this whole algorithm in place. If you want to make whole algorithm in place, then you need to avoid recursion, because recursion may use that stack. The memory used by the stack could be too large. So if you want to make in place, then you can convert this recursion to iteration. Do conversion. Iteration. Here it's not too hard. But at the beginning, we only want to make sure the correctness. So we can solve the problem. So at the beginning, we want to focus on the correctness. So we can use recursion at the beginning. Okay? After you make sure everything is all right, then the next round, then you want to convert it to the iteration way implementation to save your memory space. Here, this Heapsort, all these operations, we can convert it to non-recursion way, the iterative way. All right. Yeah, so let's write a pseudocode to do the detection and the fixing operation. Yeah. First, we need to do detection. Yeah. First round, detection round. Second round, fixing round. Yeah. All right. Now detection. So we do comparison. We compare the value A of I and A of 2i. If A of I less than A of 2i, then we find a violation, right? Yeah. If this condition is satisfied, that means we detect one violation right here. Yeah. After the detection, we need to store the array index 2i in this temporary variable we call the largest. Yeah. The meaning is, yeah, because eventually we want to make the largest value stored in its index number, index location. Yeah. Because after the detection step, the result, the number stored in this largest variable is the one that is the node that hold the largest value among the three nodes in this triangle. That's the reason we call it this temporary variable largest. Yeah. All right, so after this detection, yeah, so we store 2i in this temporary variable. Yeah. All right. Else, yeah, because else, that means A of I greater or equal to A of 2i, then we store I in this largest variable. Yeah? No violation. Else case means no violation. No violation, we just store I index, its parent, the index of its parent in this temporary variable. All right? But that's just for the left checking, right? Left child checking. We need to do the other half, right child checking. Yeah. Let's compare, but this time we use A of largest, that value, to do the comparison. Compare it. If it is less than A of 2i plus 1, that means we find another violation. So we should update the value stored in this largest temporary variable. Yeah. So we update it, yeah, by 2i plus 1 value. Yeah. All right. Yeah. Else, we do not need to change. Else, because we keep the older value, we do not need to change. All right. So this is the detection step. Okay. So far, this is the detection step. All right. The next round, the fixing round, detection and the fixing round. To do the fixing, we need to check if we really need to do the fixing work. Yeah. So if largest, its value is not equal to I, the index of the parent node, not equal, then we need to do the fixing work, right? Now, if it equals, no fixing. Yeah. All right. So not equal, then we need to do swap operation for fixing. The swap operation swap A of largest, the value, and A of I. Yeah, because it's not equal. So we need to swap. Okay. All right. So in this way, that's called, we do the complete local heapify operation on one local triangle. Okay. After that, then we need to, do the fixing globally, right? Yeah. So this is a local fixing step, but we need to complete the fixing operation everywhere in the heap. But when we do that, we need to consider the order, in which order we do the fixing operation. Because we don't want to mess up. We want to follow the right order. Yeah. After we complete a scan, yeah, so we need to scan the whole tree. we need to scan the whole tree following some order. After one scan, we can make sure we get the whole tree recovered to max heap structure. Yeah. All right. 8.4, heap example. Here I use a heap example to show you that max heap. So first, to let you see the the violation thing and how to fix the heapify. Then we look at how to build a heap. Yeah. All right. Max heapify example. All right. So in this example, you can see there is one gray node. This gray node, I use this gray color to show you there is a violation in the triangle with this node as the parent node. Yeah. Violation here. Yeah. Yeah. So we can, because at this location, this gray node location, there is a violation. Yeah. So we can call this node as a dirty node. It's not clean. Yeah. It's dirty. So we need to clean it. Yeah. We need to recover the max heap property to make it clean. Yeah. Yeah. All right. How to fix it? Yeah. Based on our local heapify operation, yeah. All right. We need to select which one has the largest value in this triangle. So this one has the largest value. Then we just do one swap operation. Yeah. So after one swap operation, yeah. So here you can see that dirty node moves down, right? Yeah, this gray node, dirty node moves down. It is still dirty. Okay. Yeah. In its older location, it is clean, but because that when we move it down, it carries the dirty information in it. Yeah, it moves down, but still it carries the dirty stuff within the node. Yeah. So we need to follow this dirty node to do all the possible fixes. Yeah. So that's why we need to keep track of this dirty node. All right? Yeah. So then we need to do the local heapify operation in this triangle, local triangle. All right. But this time we need to do swap between these two nodes. Yeah. Because this one has the largest value. After another swap operation, that dirty node hit the bottom. Yeah, because it reaches the bottom level. When it reaches the bottom level, it becomes clean. Yeah. Yeah. Any node, because when you reach the bottom level, that means there is no violation anymore. Yeah. Because the bottom level, there is no child node. No child node for this node number with value 4. Node with value 4. Yeah. No child node, that means no violation, right? Yeah. If you are only when you have at least one child node, then you can have possible violation. Otherwise, no violation. So then it becomes a clean node. Yeah. So here you get the idea. Yeah, when we need to, clean or we need to recover the max heap property in one particular location, we need to keep track of that dirty node all the way down to the bottom. Yeah. Or there is one situation you can stop before you reach the bottom. That is, if that node somewhere in the middle, you do detection, it is no violation, it is clean, you can stop. Yeah. When you do detection, there is no violation, somewhere in the middle, yeah, before it reaches the bottom, then you can stop. Yeah. Otherwise, you need to go all the way down to the bottom. Yeah. All right, so that's the local heapify operation. Yeah. You need to do it in this way. All right. Next one, this time we need to build a heap from scratch. Yeah. At the beginning, there is no heap structure. So we are given an array of arbitrary, random data, yeah, in any order. Yeah. But we need to, after a sequence of local heapify operations following certain order, yeah, the order is important, following certain order, then we can get a max heap. All right. Let's look at this example. Yeah. So in this random array, yeah, yeah, so at the beginning, we do not have any. So, yeah, I mean the values are arranged randomly. Yeah. So no max heap property. Yeah. So actually, the violation occurs almost everywhere. So you need to fix all the violations to make a max heap. Yeah. All right. When we start, first we arrange these elements in natural order. So, yeah. So here, this means our index 1. Okay. So index 0. So we do not need to write it. Yeah. We skip it automatically. Okay. So here we do not mention that. 0 location, yeah, nothing there. All right. So then, following, index numbers, so we arrange 1, 2, 3, 4, and so on. Okay, 5, 6, 7, 8, 9, 10. Okay, yeah. So we arrange the first round. We just use the natural order to arrange these nodes. Yeah. Then we do the local heapify operation following a certain order. Here I want to show you in what order. Yeah. First, yeah, when we start, we need to start from the bottom level. Okay, so we do the bottom up. Yeah, bottom going up. So bottom up way. Okay. But at the bottom level, we do processing using order from right to left. Yeah. The first time when we start, we look at the rightmost local triangle for processing. Rightmost. Okay. No violation, right? Yeah, because you check the max heap property, no violation. Yeah, so we move to the next local triangle. Then you find a violation. Here, the star means violation. Then you need to run the local heapify operation to fix it. All right. Here, after the local heapify, so this after local heapify operation, you fix that violation. All right. Then the next one, because bottom up, you finish this bottom level, right? So you need to go to the next higher level. But you start from the rightmost local triangle, and you detect the violation. The star means there is a violation detected. Then you run that local heapify operation. You need to swap these two, yeah, and you fix it. After that one, yeah, still in this level, yeah, from right to left. So you need to process this. Those, all right. Then you need to do the swap, right? Yeah. But when you do that swap, yeah, you need to do all the way down to the bottom, right? Yeah, because there's another violation. Here I just complete that fixing step. Yeah. So you finish this triangle. You finish this triangle. Then you move one level up from right to left. So you need to work on this triangle. Then you'll find another violation. So then local heapify swap between these two nodes. All right. Then after that, another violation, you need to keep track of this dirty node. So this is the dirty node. Keep track of it. So another swap between these two nodes, yeah, and another. Yeah. When you reach the bottom, it's clean. Yeah. Because you already reached the top, right? Yeah. The previous triangle is this one. You already reached the top. After you finish processing the top local triangle, then you are done. That means you get a max heap. Yeah. This time you can check, yeah, because our algorithm, our order, our bottom up from right to left, if you follow that order, it guarantees that after you finish all the local triangle processing, you will get a max heap. Yeah. All right. After you get a max heap, you are ready for the heap sort. Because when we apply the heap sort, we need to work on a max heap structure to do the heap sort. Yeah. So it's ready for heap sort. All right. Yeah. But before we do the heap sort is our last step. Before we do the heap sort, one important thing we need to do. That is estimate the building cost for a max heap. Building, we do not know how much cost, how much operation. Yeah. How much operation? The building cost. Okay? Yeah. How much operations do we need? If the building cost is too high, yeah, it's possible. If the building cost, yeah, you can consider how much work we need to do in the previous slide. If the building cost is too high, then we may want to stop. Yeah, because the whole algorithm will be very slow. That means this method is not a good one. So we need to consider a different method. Yeah. So this step is important. Only after our estimation of the cost, we feel it's acceptable. Yeah. So this much cost is acceptable, then we can continue. Yeah. Otherwise, if it's too high, how much is too high? Here, let me give you some idea. If the cost is big theta of n squared, that's too much. Because that's already the worst case of some very bad sort, right? Selection sort, bubble sort, insertion sort, the worst case is big theta of square. If your building cost is already corresponds to the worst case of those slow sorts, yeah. Those sorts we treat as slow sorts. Selection, bubble, yeah. Yeah. Insertion for the general case. Yeah. Insertion sort for near best case, then it's really good. But if it's not, then near best case, yeah. Average case, still very slow. Yeah. Then, if the building cost is this bad, then we do not need to continue. We should stop immediately because not worth it. Yeah. So that's why our next step also important. We need to estimate the building cost. in order to estimate the building cost, we need to do this topic 8.5, heap nodes in each level. We need to do the counting. We need to count. Count the number of heap nodes in each level. Yeah. But here, when we talk about level, in different situations, the definitions of the levels could be different. Yeah. Because this is this term is very vague. The level, meaning of the level is very vague. Okay? Yeah. With respect to what number you call it a level, right? Even the level, there is a direction factor. The level you count from top to bottom or from bottom up, right? From top down or bottom up. Top down, you have certain levels, right? And the bottom up, you have certain levels. And even bottom up, you can still use different definition for the levels, right? Yeah. So for that reason, there are some concepts related to this level number. Yeah. It could be different in different cases. The meaning is different. Yeah. All right. All right. So now we consider. So here we do the bottom up. Yeah. So here we do the bottom up. All right. Yeah. All right. Number of leaves in a heap. First, we define this leaves. Yeah. Some of you can recall, yeah, because in your discrete math, you have some, basic graph theory topics. Yeah. Yeah. So here, let me just refresh your memory. First, let's consider the meaning of leaves. Yeah. Because here we study trees, right? Binary trees. When you have trees, you have leaves, right? The leaves in a tree, that concept. Yeah. But the leaf nodes, these are the leaf nodes. Leaf nodes, those nodes without any child node. Yeah. If a node has one child node, then we cannot call it a leaf node. Yeah. Yeah. So only those nodes with 0 child node, then we can call it leaf node. So here, in this example, there are 5 leaf nodes. Yeah. All right. Yeah. All right. Yeah. Then, the question, our first question you need to answer, given n nodes, so the total n nodes, yeah, in a heap, n nodes, given n number, how to find the number of leaves in this heap? We need to answer that question first. Yeah. We need a formula. Formula that tells us the number of leaves in this heap. To answer that question, so we studied parent-child relationship. Parent-child relationship. Right? Child here, we use left child. Yeah? Because if a parent node has a child node, it must have a left child, right? It may not have a right child, but it must have a left child. Yeah. So for that reason, we can consider if the parent node corresponds to element A of I, then we want to study its left child, A of 2I. Yeah? Because A of 2I plus 1 may not be available. But A of 2I should be available if it has a child node. Yeah. All right. So this relationship. All right. Now, I want to ask you how to find some condition for a leaf node. How do you know a node is a leaf? Based on our understanding of a heap. Yeah. How to tell? Yeah. If I give you the index of a node and the size of the heap, n is the size of the heap. I also need to give you the size, n number, and then I give you the I number, index I number. Now I want to ask you, is the node A of I is a leaf or not? How to see that? Yeah, that question. Yeah. If we can answer this question, then we can figure out the number of leaves quickly. Yeah. All right. Here there is a critical condition you need to figure out. Critical condition. That is, yeah. So when you consider if A of I, if this node is a leaf, first you double this index I, 2i. When you double that I, 2i, it is out of the range for the nodes in this heap, out of the range. Because your heap nodes has a range, right? Yeah. Range for your heap nodes from 1 through n. Yeah. The smallest heap node is index is 1, largest is n. When you double I, you get out of the range. So 2i is strictly greater than n, then it's out of range. If 2i is out of the range, that means A of I is a leaf. Because its potential left child is out of the range. So no left child, right? Yeah, because if 2i out of range, it means A of I has no left child. If A of I has no left child, then it's a leaf. That's simple. Okay? All right. So out of the bound, yeah. Yeah. So no child. Yeah. If it's out of bound, yeah, that is 2i is strictly greater than n. Okay? Yeah. But I is within the range, right? I is within the bound. So I is less than or equal to n. In this way, we can find appropriate range for index I. I should satisfy some inequality related to n. Yeah, so let's write that part. Yeah. All right. Yeah. So this is the index range. Yeah. Then we solve inequality n over 2 strictly less than I. Yeah. Yeah. And we need to find the smallest such I. Yeah. Smallest such I. Strictly than that. Okay? Yeah. So the smallest I is this expression. Flow function of n over 2, then plus 1. Okay? Yeah. Yeah. Plus 1. Because this number is strictly greater than n over 2. Okay? Yeah. So for that reason, so the smallest I is this number. Then what's the largest I? Largest I easy, right? The largest I, that's n. So we can find the range for I with the lower bound and upper bound. If the array index I falls into this interval, then the corresponding node is a leaf node. That's simple. It's a leaf node. Okay? All right. Yeah. Now, next question. Yeah. So now you know the range. So this is the range. Upper bound, lower bound range. Next question. How many leaves do we have? Now we need to count. How many integer i's in this range? You need to give me that number. You need to count the number of indices for the leaf nodes in this range. Yeah. When you have upper bound, lower bound, inclusive. Yeah, here it's inclusive. Okay, all right, inclusive. Yeah. Can you do the counting? Here we need to do the counting. Yeah. What is the right way to do the counting? We count the number of integers in this range. That's our next question. Okay? All right. Here, because we do not have much time, so I need to complete this quickly. Yeah. All right. If I draw a diagram here, yeah. So you have lower bound. This lower bound is n over 2, floor function plus 1. Now you have upper bound. Upper bound is n. Yeah. So all the integer between these numbers, they are valid indices for the leaf nodes. Yeah. All right. So all these numbers valid index numbers. Now I ask you to count the number of integers in this interval, but include 2 endpoints. Inclusive. Yeah. Include 2 endpoints. Yeah. How to calculate that? Yeah. The way to calculate. Yeah. All right. You need to do subtraction. When you do subtraction, make sure you do not subtract away this lower bound. Because you need to keep the lower bound. You do not throw away the lower bound. Yeah. How to keep the lower bound? Okay. When you do subtraction, you use the upper bound. Upper bound is n minus. All right? Minus, but you need to keep the lower bound, so you should not subtract the lower bound directly. You should subtract the integer 1 smaller than the lower bound. So you need to do this subtraction. 1 smaller. Yeah. Because that number is out of the range. Then you can safely subtract it. Take it away. Yeah. Take it away. Then you keep the lower bound in the counting. Yeah. Yeah. So the answer is this. Okay? Yeah. All right. Answer is this number. N minus floor function of n over 2. Yeah. But this function has another equivalent formula. Yeah. Ceiling function of n over 2. If you want to simplify it a little bit, it's the ceiling function of n over 2. Yeah. So this formula is given in our textbook. Yeah. All right. So I need to finish quickly. Yeah. All right. Yeah. Yeah. And yeah. So based on this formula, we can write another expression. Yeah. So you have 2 expressions. When you calculate the number of leaves, you can use either one. Both correct. Yeah. And then this formula can be proved. Yeah. Because some of you, so how do we see it? If you want to prove it, then it's even easy. If you want to prove it, you consider n is even, n is odd. So you do verification. You verify this formula with two cases. N is the even case, N is the odd case. Then both cases correct, then it's correct. Yeah. All right. So we complete. So we finish this, even case. Number of leaves. Number of leaves. Yeah. All right. So let's stop right here. Next time I need to remind you, our Monday next week, that's August 4th, right? Yeah. August 4th, Monday, we change to online course, online meeting, okay, Zoom. Yeah. Yeah, because on Wednesday, we need to meet in the classroom. Yeah. So I don't ask you to come to the school twice a week. Yeah. So I only ask you come to school once a week. So I will post announcement. Yeah. So for all the students in the class, I will post announcement. We will meet on Zoom on Monday. Yeah. All right. Then we will meet in the classroom on Wednesday. Yeah. All right. See you on Zoom Monday next week. Yeah. Oh, make sure. Regarding the homework assignment number 2, although I didn't give you a chance to ask me questions, but I plan to do some hint videos. I just based on my understanding, relatively hard question, I will explain a little bit. But if you want to give me any information, let me know which one you want me explain. Otherwise, I just use my personal experience. Which one I feel relatively hard for you, then I give you some hint information. I record it in a video. Okay? Yeah. So in that way, I hope, but this time I hope many of you can study the hint videos to do better in this assignment. Yeah. The first time, many students didn't study the hints. Yeah. All right, that's it for today. Yeah.